This work is entitled Multimodal Fusion for Depression Detection. Assisted by stacking deep neural networks, depression is a psychosocial disorder that produces mood alterations characterized by profound sadness and a strong sense of hopelessness. In advanced stages, it may predispose patients to suicidal thoughts. Nevertheless, it remains neglected. There is difficulty in discerning symptoms due to similarities among different conditions. Nevertheless, it is a form of psychological suffering that can be anticipated through verbal and nonverbal aspects. In this sense, the analysis of audio, video, and text, such as acoustic characteristics of speech, rhythm, frequency, and intonation, as well as more downward head and gaze angles and reduced eye contact, and specific language patterns, such as increased use of absolute terms, first-person pronouns, higher frequency of negative words, and lower use of positive words can provide important cues for the process of automatic depression detection. Based on these premises, the present study aims to provide a multimodal model that combines information from audio signals, visual features, and word embeddings for automatic depression detection using an ensemble stacking of deep neural networks. In addition, strategies are adopted to reduce biases, excessive variance, class imbalance, and high data dimensionality. This work uses the DAIC-WOZ dataset derived from the AVEC 2016 challenge, consisting of semi-clinical interviews in audio, video, and text. In pre-processing, visual descriptors of pose and gaze were extracted using open face, yielding unified 18-dimensional vectors per frame. For audio, after the removal of the virtual agent's speech and prolonged silences, male frequency cepstral coefficients, MFCCS were extracted at multiple sampling rates with data augmentation techniques. In text, the agent's interactions were excluded, and the dialogues were normalized and represented by word-to-vec embeddings. Thus, each participant is described by a concatenated multimodal vector integrating audio, video, and text information. The proposed architecture schematically represents the entire system workflow. The process begins with unimodal data pre-processing, video, pose, and gaze extraction, audio, MFCC extraction, and text generation of word-to-vec embeddings. These representations are then fused into a joint vector that serves as input for different deep neural networks composed of fully connected layers via regularization using dropout and specific activation functions. From this point, the output vectors of each DNA are obtained, represented by reduced dimensions. For this end, a function is responsible for loading a list of models and the original dataset, generating individual predictions. These predictions are then combined into a single structured dataset suitable for feeding the stacking metamodel. The metamodel therefore receives the low-dimensional vectors resulting from the DNNS and performs the final training, producing a binary classification of individuals, labeling them as depressive or non-depressive. In the experiments, SVM-SM-OTE was applied to oversample the minority class, considering the imbalance present in the data. The tests were conducted by varying both the techniques and the number of DNNS used in the metamodel. In order to evaluate different scenarios, unimodal approaches, audio, video, and text were explored individually, as well as multimodal ones, combining pairs or modalities, enabling analysis of the impact of modality fusion on depression detection performance. Here we present a summary of the experimental results. Table 1 compares previous works with our stacking DNN approach, showing consistent gains in metrics such as accuracy, recall, and F1 score, especially in the combined modalities. We observe that while previous works exhibited limitations, fusion via stacking managed to maintain a balanced Betty wins. Precision and recall, achieving robust values in both the validation set and the DAIC-WOZ test set. The images reinforce these findings. An AUC of 0.91 indicates excellent discriminative capacity of the model, and the confusion matrices show good performance in the correct identification of classes, with emphasis on the development set where recalls was excellent. In summary, the results show that the stacking approach offers meaningful improvements over the state of the art. In this work, we presented a stacking ensemble with 3 DNNS treated as strong learners, which achieved a degree of separability greater than 0.9, confirming the effectiveness of the approach. For future work, we intend to expand the experiments by incorporating 2D and 3D facial landmarks in the video modality, in addition to exploring new representations for textual data and audio signals. Another promising direction is to integrate more robust deep learning models into the stacking framework, such as LSTMS, to capture temporal dependencies. Finally, we plan to extend the investigation to other disorders such as anxiety and post-traumatic stress disorder, as well as neurodegenerative pathologies, including Alzheimer's, Parkinson's, and molecular causes.